Welcome back to Akbar Academy, where the deeper you look into physics, the more it stares back with surprises. I'm Kaleem Akbar, and today we're tackling a topic that affects literally everything: thermal properties and temperature. To explore it, I'm once again joined by two of the greatest scientific minds in history: Sir Isaac Newton, master of mechanics and classical physics, and Professor Albert Einstein, the man who redefined energy, matter, and everything in between.
Always pleased to return, Mr. Akbar. Though I must admit, when I think of heat, I still recall my early experiments with light and prisms. But your modern understanding, far more precise.
And far more useful. Temperature is no longer just a sensation. It's a measurement of how wildly particles are dancing at the microscopic level.
Well, speaking of dancing particles, here's a fact to heat things up. In summer, the Eiffel Tower grows about 6 inches taller, not because of magic, but because of thermal expansion.
Thermal expansion. When a solid is heated, its particles gain kinetic energy and vibrate more. This causes them to push farther apart, ever so slightly, resulting in expansion.
But not all materials expand equally. Metals tend to expand significantly, whereas materials like glass or ceramics expand far less. It depends on the bond strength between particles.
And gases? They take the prize for expanding the most, then liquids, then solids the least. It's all about how much room the particles have to move.
Exactly. Gases are already spaced out, so adding energy makes them spread even further and faster. That's why heat causes your car's tire pressure to increase in summer.
And this expansion must be accounted for in engineering. Those gaps you see between slabs of concrete on sidewalks, they're expansion joints designed to prevent cracking as the material expands and contracts.
Same goes for bridges and power lines. Engineers leave deliberate slack in cables, knowing the metal will contract in winter. Without that slack, they could snap under tension.
And let's not forget one of my personal favorites, the bimetallic strip. Two metals bonded together that expand at different rates. As temperature changes, the strip bends, perfect for thermostats and fire alarms.
A clever mechanism indeed. The differing expansion rates convert heat into motion, a mechanical response to thermal input.
But then we come to water, which as always breaks the rules.
Water is an oddball. Most materials become denser as they cool, but water, it reaches maximum density at 4 degrees C, then starts expanding again as it freezes.
A truly remarkable anomaly. Frozen water is less dense than liquid water, hence ice floats. Were it otherwise, lakes and oceans would freeze from the bottom up.
Which would make life on Earth pretty impossible. Aquatic life would struggle to survive harsh winters. That one strange property, it helps protect ecosystems.
And it links beautifully to another concept: specific heat capacity. The amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius.
Water's specific heat capacity is about 4,200 GKGE, one of the highest out there. That's why oceans moderate Earth's climate. They absorb heat slowly and release it slowly too.
It also means heating water, whether in kettles or power plants, requires a great deal of energy. This fact is essential when calculating energy transfers.
Which brings us to how scientists measure all this. Enter the calorimeter, an insulated container used to calculate energy changes during heating or cooling.
Indeed, the trick is preventing heat loss, but even the best setups lose some energy, usually to the surrounding air or container walls. That's why experimental values often differ slightly from theoretical ones.
As we say, no system is perfectly isolated. Energy, like water, always finds a way to leak.
And when you consider extreme environments, like spacecraft, these thermal principles become even more critical.
Yes, one side of a spacecraft might face the sun at hundreds of degrees, while the other side sits in shadow near absolute zero. Engineers must account for both.
Thermal insulation, radiators, heat shields, all designed with this in mind. The stakes are far higher than a cracked pavement.
Yet even in our daily lives, these ideas show up constantly. Why tire pressure varies, why glass shatters when heated unevenly, why metal lids are easier to open under hot water.
and why thermos flasks are double-walled and vacuum-insulated to slow down heat transfer by conduction, convection, and radiation.
From morning tea to nuclear fusion, it all connects back to temperature and particle motion.
And when you grasp that, the world changes. You stop seeing objects as things and start seeing them as swarms of particles in constant interaction.
Every material, every structure, every invention starts with understanding how particles behave under heat.
So whether you're an engineer, a student, or just someone wondering why your window panes rattle in the summer, it's all thermal physics. And here at Akbar Academy, we believe understanding heat is cool because we are always Akbar Academy, a class above the rest.